Welcome, everybody. Short technical problems. Today I will present the scaling Xen HVM Guest Beyond 128 vCPUs. My name is Julian. I work for Vartis, and this was one of the tasks I was assigned to when I joined the company some time ago. It's cropped. Okay. But how can we go beyond 128 vCPUs on HVM guests? And this is what we explore today. I discovered several issues currently in Xen which limit the number. Basically, there are two. One is related to I/O requests, and the second issue is a little bit bigger. One is related to X2 APIC and its IDs, or like the X APIC and its IDs, and this has several sub-issues, let's say. First of all, let's look at the I/O request problem. Currently, how it works in Xen, there's the DOM 0, we have Xen below, and then we have several guest domains, in this case, only one. There's the I/O request server below here. This one maps some shared memory into DOM 0, and then it has several event channels in order to signal the DOM 0, the device model running in DOM 0. And we have the user space domain, which when it accesses some I/O, it will trap into Xen. And the I/O request server will then write the request into the shared memory and will signal the device model in DOM 0 via the event channel, which then handles the request. And then when it's done, the result will be obtained by the I/O request server from the shared memory and then basically returned to the guest. This is transparent for the guest. He basically traps. He doesn't see that this instruction actually falls. In the background, it will be handled, and then the result will be passed to the caller. There are two types of I/O requests. There's the buffered I/O request, which is like a small write-only PIO for PIO operations, and then there's let's say the full I/O request. The first one is quite simple. It's basically when a guest wants to write to some memory via PIO. Basically, it writes to a ring buffer, and then the guest directly resumes, and in the background, then the device model handles the request and writes to the memory that it needs to be written to. There's no return value or something. And then the second one is the, let's say, full I/O request, where we have one I/O request slot per vCPU. The guest, again, it traps. Xen writes the request into this vCPU slot of here into this shared memory. And then the device model handles the request, writes the result back into shared memory, and so on. And then the guest resumes. And here's already the crux of one of the issues I discovered. There's one I/O request per vCPU in this shared memory. And this shared memory is mapped from Xen into DOM 0 via, so basically DOM 0 requests this memory via Xen foreign memory map resource. And so, the issue is that there's exactly one single DOM heap, domain heap page, which contains all the I/O requests, one after the other. So we have simple equation. Basically, we have 32 bytes per I/O request, and we have one single page of 4K, so gives us 128 slots. So we are currently limited by this, by this number, let's say. So what we would have to do is to basically allocate multiple pages. Currently, it exactly maps one page. And there's currently no mechanism in order to map multiple pages. So this needs to be extended in order to support this. This was one of the problems. Like the first one, I implemented some prototype in order to have multiple I/O request pages for guests, so he can open more I/O requests or has more I/O request channels for the guest. Then the second problem, this is like a little bit bigger one, and I will start with a quote. Some might remember this one. I rephrased it a bit on the top. So 8-bit domain IDs ought to be enough for everyone. This was maybe some Intel engineer who said this. Yeah. First, some brief overview. What's the APIC? This is the Advanced Programmable Interrupt Controller. Each Intel core has one of them. It's responsible for what is written, interrupt delivery, IPIs, and there's written APIC timer. So there's a timer in this interrupt controller as well for timekeeping. So how does the interrupt routing work? There's the interrupt routing hardware, which matches these APIC IDs against CPU cores. So if you want to send an interrupt to another core, you write into your interrupt command register, you write the ID of the core you want to send it to, and then you fire the interrupt, and then it arrives at the right core. There are two modes. There's the X APIC. This is the, let's say, legacy mode. And then there's the X2 APIC, which is like a newer version or like an extended version. The X APIC is still, I mean, since it's not legacy because it's still the default. So basically 99% of CPUs when the system starts, it's in X APIC mode. And then there's in Xen, of course, in order to support to give the guest a representation of this APIC, there's the vLAPIC, which is the virtualized APIC. And this one is already fine because it supports as well as guest X APIC mode and X2 APIC mode. So we are good on this front. So now what's actually the issue here? Because we have already X2 APIC support, which is the extended version, which supports up to 32-bit IDs. But still, like the X APIC already has 8-bit IDs. So in general, we should be good because we have 8-bit, which gives us 256 IDs, which is more than enough to support more than 128 vCPUs or CPUs. But this is unfortunately not the case because this is the code in Xen. And this is for, let's say, legacy reasons as well, because usually the APIC ID is the vCPU ID times 2. Because this has the reason for this is that usually cores are packaged when they are packaged with hyperthreading, for example, they have like 2 threads, and the core 0, thread 0 has then APIC ID 0, and the core 0, thread 1 has then APIC ID 1. So the next core gets APIC ID 2. And this is why we need double the amount of IDs in order to support 128 vCPUs. So in general, we need X2 APIC support. Here below, yes, sorry, there's a piece missing, but okay, doesn't matter much. In the beginning, this was like the original in X APIC mode. You have this ID register, which was only 4 bits for very old Pentium processors. Then Intel extended it to 8 bits, which is from bit 24 to 31. And then in X2 APIC mode, you basically have a register with like the full amount. So we have 32 bits of ID space, let's say, which should be enough for everyone. Let's see. So yeah, what is actually the problem? Because we have X2 APIC support, and also this virtualized APIC supports X2 APIC, so there's no problem, right? But there's more to this, because we have let's say the boot sequence and this MADTs. How does it work when the system boots? There's the BSP, the boot processor, which starts up, which has usually APIC ID 0, so we are fine. It never happens that like the BSP has like an APIC ID beyond something. It's usually 0, so there's no limitation. We don't have a problem with this one. And then happens the topology discovery. This happens in the ACPI code. There's basically these ACPI tables which give information about the system. This is like a linked list with there's the root descriptor, and then it points to different entries. There's also for battery and all kinds of stuff, like everything this ACPI describes is in this table. And there's one table which is called MADT. This is a multiple APIC description table, which basically describes all the APICs that are in the system. And there are different types. Originally, there was type 0, which is for the classical X APIC, which has, again, an 8-bit ID field in order to describe all the APICs in the system. And recently there was, or like recently, I don't know exactly when, but afterwards, the specification was extended in order to support this type 9, which is X2 APIC support. And currently, this ACPI specification 4.0 for the X2 APIC is missing. And of course, it's the obligation of Xen to craft these tables for the guest. But currently, yeah, we lack this entry. So basically, Xen cannot inform the guest that there are APICs in the system with IDs higher than 255. So we are again limited by this 8-bit ID. But let's assume we have this APIC like the type 9 entries. Then what happens next is basically the BSP sees that he has like very big amounts of IDs or like APICs in the system. So he will switch to X2 APIC mode. And yeah, this is a critical step, of course, because otherwise, I mean, if he then tries to send to other APICs and he's still in X APIC mode, he would not be able to. So he switches to X2 APIC mode. So his like interrupt, here this one, the interrupt command register contains full 32 bits. So he can send like IPIs to wake up the other cores to higher core counts, like to higher core numbers with higher APIC ID. Because, yeah. And then afterwards, when the AP wakes up, like the application processor, this is like a secondary core. In the beginning, because he starts also in X APIC mode, so his ID register will be also 8-bit. But in the beginning, so this one will be truncated or contain an invalid value. So he has to switch also to X2 APIC mode. He writes to this base register the extended bit, and then he will switch to X2 APIC mode. And only after switching to this mode, he can read its ID to have the full 32-bit. Yeah, here this is the interrupt command register for the X APIC. You see the destination ID, destination field. Does this work? It's this one. Is only 8-bit. And then here in X2 APIC mode, we have like the full 32-bit. But this MADT, this multiple APIC description table, is actually not enough in order to enumerate the CPU topology. There's some extra code, which is related to the CPU ID instruction. Basically, before switching into X2 APIC mode, there's the CPU topology, which gives additional information about the structure of the core, let's say, because with this APIC ID, it's just a linear ID, and he doesn't know whether there's like, let's say, hyper-threading, so there might be multiple threads in one core, and there might be multiple CPUs in one package. And this is important for like if there are multiple cache domains and all this. So all this hierarchy description is lacking from this ACPI code because it just gives linear IDs. So this information to probe the hierarchy of all the cores and so on, this is in the CPU ID code. And currently there are two enumeration, let's say, modes. You can request CPU ID with leaf 0x1 or 0xb, which is or 11, which is again this extended mode in order to enumerate in X2 APIC mode. Yeah, you see here this one. Basically, it needs to call CPU ID instruction with B in order to get the full IDs again. But currently, in Xen, the CPU ID code returns EBX0, which signals basically this leaf is unsupported, and you should fall back to leaf 1, which only again has 8-bit IDs. Yeah, this is like from the reference manual. Whoops, shit. Okay, you see here, there's the, do we have leaf 11? Yes, then go this way and enumerate system topology using CPU ID leaf 11. This is the more complex, or like the complex one. And if not, then use this one. And this is CPU ID leaf 1, which again shows the return value only has like 8-bit. So we are limited by this ID. And this one, yeah, is the full, the CPU ID leaf 11 gives like full X2 APIC ID. And this CPU topology code is also currently missing in Xen. Yeah. So this would need to be added as well. And the last point is MSI and RTE routing. RTE is like, it's a legacy mechanisms like redirection table entries for the IO APIC. And MSIs are like the message signaled interrupt. How this works is basically devices write, PCIe devices can write to a magic address, which is this FE, and then below are additional information. They write into this range, and then the interrupt hardware decodes and sees this write, decodes bits from this lower region here in order to know to which core to send the MSI. And again, in this address, there are bits 12 to 19 to give the ID to which to send this MSI to. And again, this ID is 8-bit. So yeah, it doesn't work, because then even if we have like more than 128 vCPUs created in Xen and we start Linux, Linux will just see that there's an issue with because it cannot send interrupts to these cores, and then it just refuses to bring them up. So yeah, you will just get an error. So yeah, this is a limitation. But there's already half of the solution is there, because there's actually this Xen HVM CPU ID extended destination ID. This is like a flag which can be exposed via CPU ID to a guest in order to tell him that there is additional bits in this address. Oops. Yeah. So basically, in this address here, additional bits can be used in order to send to extend the destination ID space. So basically, these additional bits can then be used for decoding in order to address APICs in a higher range. So which gives us 15-bit of destination ID, which is 32,000 APICs. Basically, this is all on Xen side. This is all implemented in software. So this decoding happens then in Xen, this address. So actually, we could do whatever we want because this is all written in software, let's say. But there's a kind of specification, but it was proposed by Intel in their I/O controller hub in the past. Is from 2002. They had like already proposed to use extended bits here in the MSI address for to support higher APIC IDs. In the beginning, it was actually the bits 11, like 4 to 11. But then later they saw in the later specification they needed an additional bit, so 1 bit was even chopped, and now it's only 7 additional bits, which gives us still 15 bits of addressable APICs. And then there was a commit in Linux kernel from 2020 from this guy Woodhouse who had this whole idea to do this. And then in Xen, the flag was introduced, which is this CPU ID extended destination ID. But currently, there's still the part missing that QEMU, which handles the MSIs and so on, support this extended destination ID bits. Yeah. And of course, there's more. I tested, I think, up to 160 vCPUs in a Linux HVM guest, which worked. But then when I tried higher vCPU counts, it failed. So there's surely more work ahead. And yeah, let's see. Thanks. Yes.
Do you want to take some questions?
Yeah, sure.
Questions? I got a couple. Start here and I'll go to the back.
Yeah, the first question is about the 15-bit destination ID. Is there any way to signal that to VMs that are not Xen aware, like Windows, for example? The Windows kernel by itself is not really aware. So is there any way outside of Xen CPU ID?
I don't know, actually. Yeah.
We'll bring this into the back for the Zoom room here.
David Woodhouse is at Amazon, and he has persuaded even the Windows kernel to know what that means under Xen. So that extended APIC ID bit is known to the Windows kernel. It's known to FreeBSD as of H2 last year.
Oh, okay.
So it knows what that is.
Okay.
Is that a specific flag also?
Yeah.
Okay.
So quite early in your presentation, you said that you needed to go straight to X2 APIC mode. That's not actually true. The thing in Xen where it takes the APIC ID and multiplies by 2 is a bug. That's a straight up bug.
Okay.
If you look back far enough in the history, so on early systems, the BSP didn't have the ID 0. You had to have that ID for the IO APICs when they were in 3-wire bus mode. And Xen had logic to reserve 1 ID for the IO APIC back in the very, very early code added in. And that bug has been propagated by a whole bunch of people not knowing that it could actually have been dropped 15 years ago.
Okay.
You can't, it's not quite that easy these days, because if you just drop it, you will break migrate. There is a series out on the list from Alejandro trying to fix this in a better way, but it's just adjusting the topology. Once we have fixed that bug, once we fix that bug with the topology and the changes to the IRX server, you can go up to 254 CPUs. All the other X2 APIC on top of it, yes, we do need to do that as well, but that is harder still.
Okay. Yeah, I didn't know. I thought it was actually for the hyperthreading case where you.
Yeah, but you can tell the CPU there are no hyperthreads so long as you get the CPU ID information correct with it. It's just that everyone looks at that and thinks it's the same thing that KVM does to hide hyperthreads, and it's not. It was an IO APIC bug, not a hyperthread bug from a long time ago.
Good to know. Thanks.